Just want to make sure you can hear me. Okay. So the sound is clear. Put everything back and start doing our thing. So last time we left off with our computer architecture, but it's not perfect because we just sketch it out. And this control flow things and the other stuff, I actually forgot about it because it's been a week or something. So we need to look over it a bit before we can clean it up. Yeah, I need to close it. What are you doing? Actually, I got the webcam on. Alright. What a interesting stream. So we have to draw this again. What's going on with this guy over here? So the most important thing that we discovered last time, we can use something like a 4-bit encoder or decoder. I don't know how to call it. Let's do some research. Encoder. Let look at the encoder versus decoder. So encoder, they take a read instead of just watching the picture. Basically convert, apply information signal into code digital bit stream. So this is decoders. What we're doing is decoder. We take some binary value and we decode it into a bunch of signal, a bunch of output that only one of it is enabled. So we have a 4-bit input. We can decode it into 16, which is a lot that we can control 16 component, like the register, ALU and the other kind of thing. Also want to create more stuff here, which is more register, and we got into a problem last time when we tried to create a multiplication program. Every time we do some I realized that when we do the addition, we have to store the value in our VRAM first before we subtract our second value. So we have to go back and forth with the RAM, which is not very efficient. So we need a way to let the ALU doing the operation with the number itself, like A doing the add with the A itself or something. We need to add another instruction here, like add So the add instruction doesn't have sub op. It doesn't have sub opcode, but right now we can add it. We can give it the sub opcode, which tell what should it do, like A add with B, or just A add with A itself, or something like that, or B add with B. And maybe you have more register, and I want to generalize the write enable and the read enable right here. So the read and write enable is, we can use tri-state buffer in the input. So maybe we need to start drawing it again in a cleaner way. And also this control flow thing, we also want it to be a set of microcode so that we can change it whatever we want. And I don't know, like, how can we set this in our computer. So we need to, the purpose of this stream is to clean everything up, but right now I forgot what we did in the last stream, so we have to review, and I don't know what's going on. So let's start with our RAM. But what if we use some program that we can do it clean, more clean? Then we can use Figma. Okay, new design. So we have RAM. Where is it? So we have the RAM manager. Basically, it take a address, store it into a register before we can read or write enable our actual RAM. But what if we use Figma jam instead of this? This is not good. Let's use the jam. This one is more easy, so delete it. So we have RAM manager, and we have the instruction RAM and VRAM. The value RAM, I don't know why I call it VRAM. The value RAM, it's not right. So what is this? So we have two other chunks of RAM. instruction RAM and value RAM. Let it store basic value that we need to do some instruction. Put in a different color. So bright. Put it on red, this one put it on blue, and this is just a neutral. So basically this is our bus. Which is 8-bit. So VRAM connect to the bus. The RAM manager have to connect to the bus. Yeah, just put it there. Oh god. And we have this instruction and value RAM. Program counter. Go into program counter. Program counter is this control unit. Unit program counter. So this RAM manager and the two chunks of RAM is just like their connection doesn't connect with all of this other component, so we can ignore it for now. But what we know is that it's going to connect to all of it. Another one. Yes. One of these will enable the chip. The read and write enable. Where I put it here. This is strange. We can have another thing called tri-state buffer. This tri-state buffer. It's not connect. Yeah. So basically the tri-state buffer just working as a write and read enabler. So if there is data in our bus, it will not flow into our RAM until we enable the tri-state. So our tri-state has two input. Another one. How do I connect it? Green. Let's put it two different color. Put it one this. So this is the write enable and read enable. Basically, is it going this way or that way, the other way around? Why are they so big? Just delete it. And this one is for if we want to use the VRAM or not. So gotta put it on red. So that is basically the VRAM enabled or something. Put it two different blob. So that's basically what we have right now. Let's go on with this program. Wait, we can add text. Oh, that's cool. So this one is write enable, this one is output enable. So cool. And this one is VRAM enable, the second one. So if we enable it, our RAM manager will enable our value RAM. So whatever we do with it, it doesn't matter is it write enable or output enable, it will work only with the value RAM. And there is a problem right now because our output and write enable is on. It's like on the other side. It's not have any contact with the RAM manager. So if you want our RAM manager to tell if you want so complicated. I don't think we can use tri-state buffer. Let's talk about our RAM real quick. So our RAM has address, which is 8-bit or something, 8-bit address, and we have output. I'm not sure about it. So we need to find a RAM that we can use. Let's say that we have output and input. Then we have the write enable and read enable. Write enable and chip enable. Chip selected. Wait, where did I find it? I think we have another sketch. Project. This one. Right here. So all of this is chip selected. It doesn't. Oh, what is going on? Let's search for 8-bit RAM. I see. There you can. All this, there's no RAM at all. Just sell some other stuff. we can go to our, what's this one, where's the, here, 8-bit computer, schematic, RAM module, yeah. So our RAM module has input, we have address, we have write enable, chip selected, and what is this? No description, so we screwed. Let's go to a different, so this one. So we have the write enable, and the output enable is automatically out, so address, additional bit, but and this is our input, this is our output. So let's pretend that our chip's going to have a different input and output, like it's not connected to each other. So now we can, where's my, wait, oh god, did I just close it? Here. So we have input and output, it doesn't really matter. Chip selected, so if you select it, we give the address, the output will automatically output some value that inside the address of the RAM. But if we put the write enable, it will change the value. Where's the input then? Let's see some example of a 74189 chip data sheet. Here's data sheet. This one. Wait, what's going on? Is it? No, it's not. 74 LS. So this one used by Ben Eater. I don't know how to pronounce his name, but he used these chips of RAM. That's not, oh wait. Okay, this is more clean. So we have the address, we have the D. What is D? D. It's hard to see right now. Write enable, chip selected, address, output, and D. So we have a address, output, and D, which is input, I think. Copy it, duplicate it, use this D. Just pretend it is 8-bit for now. So input, so D is input. we have what they have. This. Yeah. So we have like the input and output are separate. They're not the same pin. And the output is automatically out, so we need to use like I'm gonna use tri-state buffer. I don't think we need to. So the output will overwrite our input right here. It's both way. For example, if we want to make it collectively, if you want to read our instruction RAM, we have address of something, address 000, so the value will be automatically inside our bus. And if we write enable it, oh, that's not going to work because that's not what I'm looking for. So I'm going to delete this tri-state buffer. So our input is here. Write enable. Read enable, basically it's output enable. So these two need a different color. I'll change it to blue. This is red. So these two, write enable and read enable, they just automatically directly connect to our instruction RAM and value RAM without any other component. So it just directly connect to our thing. Another one. It's a blue one. Let me do nothing, so it's more better to look at. This is how our RAM would work. So if we put the value RAM enable, which is right here, that will connect up. Maybe we can draw a RAM schematic. Should we or should we not? Let's not care too much about that. The chip enable. chip selected. Make it red. Oh, this is weird. Yeah, so there is some NOT gate between this and this, and AND gate. Oh, we need to enable it. So it's not going to work unless we enable the RAM manager. Let's just add the level of complexity. Let's just put it there. Just something. This is the enable. Where? So this is enable. Should be green. We have to enable our thing so that we'll select any of these chip using the VRAM. So we have to put like AND gate. So our VRAM enable have to connect with the AND gate and output something to the VRAM, and NOT gate with the AND gate to connect to instruction RAM, because it have to be opposite. If we enable the read, so if we want to read some value, for example, if I want to read it from instruction RAM, I just need to put this to 0. I give it the address in 8-bit. So the address in 8-bit will go through, and if we put like read enable and write enable, it doesn't really matter which one we going for. It's just going to store our address into a register, 8-bit register, and that 8-bit register will not go through our RAM yet, because if it input into our RAM will just output it outside into the same bus, which will like how do I say it? I forgot. Overwrite each other. So we have to enable it so that the value will be write or read. So after we put the address, we open one of this, it will store, and now we can just switch our address into 0, all 0, because we don't want to override, and then we enable it, and the value will flow out. It seems very complicated. Yeah. Now I think we're done with the RAM part. let's go into the control unit, which is a very important part for our computer. To make it bigger, design it bigger, and the text inside, so yeah, make it bold. So what we mentioned last time, I think we need another program counter, but our the second program counter doesn't need the jump operation. It's only like a internal program counter inside our control unit, so that it will work with our control flow. I think we need to make this thing bigger. What just happened? Go back. Let's remove this program counter and make this one control unit. Or maybe just we don't need to put anything at all. Make it small first. Internal, inner, program counter. So the internal program counter is the one who manage the control flow. So it's always going forward, but it will have to loop back to the start, because every time it read in an opcode, so every time it finish, so it's output enable. What is so it's output enable our program counter, the outer, the external program counter, the one that we're going to use a lot. We output it, and now whatever address inside the register inside our program counter will go into our bus. We enable our RAM read, so we enable it, the value in the bus will store inside the RAM manager register, and then we output disable our program counter. So now our bus will be empty, and we enable our RAM manager. So we don't need to enable our VRAM, because we're going to read the instruction, not the value. So we just enable our RAM, the value will output into our bus, and now we're gonna need to do something with that output. So the output is going to load into our opcode register. So in our program control unit, I think, or maybe it will load it into our micro code, like a somewhere that we can store our microcode. So this is microcode. ROM, because we're going to use like a read-only memory, EEPROM. Going to, this is where I'll, so we need to write it down. Microcode EE let's call it only ROM. So this is where our control unit will read the instruction. So we take the opcode. We don't need to store inside our control unit because it's going to be more component that we need to build. So the value from our instruction RAM will be inside this bus, and then we input it. We will connect directly to our microcode ROM. We just need to enable from our control unit to tell, oh, we have to store it still. We may have a register inside here, inside a microcode ROM, so that it doesn't lose information about the address of where is our instruction is. So, or maybe we can just, oh, we still need, yeah, so delete it. What's going on? Just connect it to this thing. So our control unit, we put it up here. It's very important. So inside our control unit we have two registers, which is opcode register, ops, opcode register, and then that opcode register will have to what's going on here. We load it into our raw opcode register, and then we have to read it from our microcode ROM. So to read it, we have a lot of things here, because we read it, we have the if it sub up or not, and that value will output into our, I think we can output it directly into our control unit. So control unit, yeah, just write normal English. And then microcode ROM. But how do we store it inside the ROM? What is the maximum bit that we can, oh, the ROM might be also 8-bit, or maybe we can put it like 16-bit or something. Come on, 16-bit ROM, EE ROM. So we can just find the 8-bit version of our EEPROM, the 8-bit, and then we connect two together, so to get a 16-bit. And in there we might have the specific bit that that carries some information about, like, is it subcode or not. And then we have the control code, which basically we need to decode it to control the component. Oh damn, this is complicated. Let's move this first. So if the control code and the sub opcode is sub opcode or something like that will go directly to our control unit, we don't need to use opcode register. So the operation code will have to go directly to our microcode ROM. And then any information from our microcode ROM just go directly to our control unit, so that we don't need to make it go back and forth with the bus. So yeah, delete this, make it somewhere here. Directly to microcode ROM. Let's change the color, make it more cooler. And this is just like it's very static. We set it somewhere. I don't know what I'm saying, but that directly connect to the microcode ROM, but we need the enabler so we enable the microcode ROM from our control unit. I'm not sure what's control unit, like the component that necessarily to build a control unit made up of yet. Make it this. Yeah, it's more clean. So and our control unit will tell the RAM. So what is control unit? So basically we can make the control unit using another program counter. That's what I'm talking about, and another set of microcode. So we have a different microcode ROM, a different one. So this one is, I think we can call it the bootloader. I don't know how they call it actually, but just call it loader ROM. So actually basically the loader ROM, it stores information about what should it enable. Like the first instruction or the first control in our flow is to enable the output enable the output of the program counter, so that it will have a 4-bit or 8-bit or something, depend on how many how complex our components are. So if you can use like 4-bit to control 16 information, a 16 component. So right now we have a 4 right here, and we still have a 12 more bit left. So our control unit will have will connect or maybe not. Maybe it doesn't need to connect directly to our loader ROM. You can put it somewhere like right there, and we have the inner program counter. So loader control flow counter. So the control flow counter will have to connect directly to our loader ROM. Control flow counter has like 8-bit register or something. Just 4-bit is enough, I think. And the output will automatically directly tell the loader ROM which instruction of control flow that we reading, and then the loader ROM will tell will connect to a decoder and then connect to a very different component. So connect this directly to that thing. Basically this is the jump. Or we can just call it next. So we can tell our control flow counter to go next, and then it will output the next address of the loader ROM. Does that make sense now? We also wanted to reset, like start from the beginning again, like right here where it go through all the microcode that run the instruction. It will have to go back to the the start of the control flow to read the next instruction. Yeah. So we have the reset. Let's put this red because it's quite dangerous if we reset accidentally. Next is green. Yeah. Our control flow, a control unit. Wait, so we need to manage the clock cycle here. We need to thinking about the clock cycle, which is very boring and annoying. Put this into yellow or something. Oh, it's so vibrant. Our control unit is yes. And then our loader ROM will connect to our decoder. What is this? Oh, this is weird. Okay, and use this kind of thing. This will connect directly to our decoder. And then our decoder just tell. So yes, security. Oh, we can rotate it. Interesting. The tick is so. You can make it smaller if you want to. Yeah. So the decoder connect to one of this. Oh, what's going on? Put a screen. So now, yeah, we just need to connect a bunch of it. Light blue. And this is light red. Yep. So the loader will connect to all of this component. Also, it will connect to our external program counter. So this microcode ROM don't need to connect to our control unit, but it will connect to the external one. So how do I put a different color? Different. Yeah, so put it green. The external counter, just call it a program counter. So for example, the first control in our flow is enable output. So one of these will enable the output of the program counter. I should write it better. So enable of the program counter. So this thing will have to connect to our program counter. Oh, what a like this. Make it light green. So when it enable our program counter output, our program counter will have to connect to the bus, or maybe not. Yeah, you don't need to connect to the bus. just an instruction to tell microcode ROM, but we also want to connect to the bus in case we want it to jump. So this is different because it's different from this counter and this loader ROM over here, but I want it to be the same so that like it has the same architecture, so that easier to think about it in case we change it anytime. So let's make it the same, nothing different. And we just need an additional input to tell it if you want to jump or something. And this one connect to the microcode ROM, and our microcode ROM just connect to a decoder and then spread out to a different component. So this is output enable. We have the increment, which is basically next, similar to this thing. So put this output enable blue. Make it point. Zoom it in. Yep. Now we have the increment, which also comes from our decoder, the loader ROM. Wait, so RAM read enable. We already connected. Output disable. The output disable is basically a new instruction in our loader ROM to tell that this wire over here is 0. So we don't need to care. Just disable it. This gray. And then we have to wait. I have to look at this. Next, the next instruction, which is the increment. I need to make this clean. Yep. Just make it clean first. Why it's not connected? So strange. Doesn't matter. What is our control unit again? Control. Oh, the control unit is clock cycle or something. Yeah. We enable the RAM. So let's try some simple. So when we start, we output enable the program counter, and our program counter will go to our Oh, it's not. Program counter is going with the bus. Get it wrong. So we're going with the bus, and then we read it from the RAM first, and then our instruction from the RAM will connect to our microcode. So it's not the same as the load the ROM. It's a different one. So put this bigger gray. So output enable something like a 0000001 or something, 00001. Yeah, we output enable our program counter, which is in the address 0, and then our program counter will output that address into our bus, and then we read enable our RAM manager. So it should be 0100 the rest. So now the address will store in our RAM manager, and then we disable. So basically the next step is all 0, because everything will be disabled and the bus will be 0, and the RAM manager will have some address in there still, so it stores some address in there. After that we RAM enable, so we enable our RAM. The value from the instruction RAM will flow to our bus, and our bus will have to go to somewhere. Okay, put this here. It's so bad design. Yeah, make this more clean. We put this into a point. Yes, so now it connects to our 8-bit bus. Make it smaller because so the bus is so small now. The value from the 8-bit bus will we have to load it into a register, but if we just wait, so the value will be inside our microcode ROM. Tell which instruction we choosing right now. We select which instruction. So for example, if we select the load A, and every single program, every instruction, we don't need this sub anymore. We should need like only the 8-bit control code, because every single instruction must have a sub opcode for the sake of simplicity. So you should just change it. Go to our microcode ROM, pick instruction, then we have to store, because we still need the sub opcode first before we can do anything with the value. So we have to store it somewhere, so we call it the micro ROM register. Microcode register mcrec, and connect to microcode register, and our microcode ROM will be flowing from here. Microcode register, do we have to enable our microcode register? Yeah, we need an enabler for our microcode register. So the program counter, give the address to the RAM, enable the RAM, you read the output from the RAM, and then the value will go into the bus. The bus will go to our microcode register, and our control unit will have to tell our microcode register to store that value. Simply an enable. They're coming. Open the door.
Outside.
So we enabled our microcode register. After we enable it, it will store the information about the address of our microcode, or the order of the instruction. It will store there, and it constantly output the value into our microcode ROM, and our microcode ROM will have to, oh crap, we need a decoder with a buffer. So after we enable our register, we have to go to the next step, which retrieve the sub opcode from our RAM. Basically, yeah, microcode, let's call it the opcode register. Opcode register, and then we have the sub opcode. Sub op register. And we have to enable one of these two. So to enable the op register, we don't enable it from our control unit, we enable it from our loader ROM. We enable it on our from our loader ROM. What's going on? here. So the sub up most likely telling the address, but sometimes it also tells our ALU which operation it's doing. So that is a bit complicated. So we have to connect it to the bus. Wait, the sub op is the sub opcode is like jump the load need the sub opcode which address of the memory we're retrieving. So we will have to connect to the bus to retrieve it from our RAM, but in the case of jump, okay, we can just put it in the AND, the add and the subtraction also. That's not good. Let's go back. Let's just say we connect this. Let's go with this one connection. Seems so weird. So this one is gray. So let's connect to our, oh god. I should have streamed this a few months ago. Oh god, I mute the entire time. Holy. So where are we? For example, the load A. The load A, we have the instruction which we have the control code. What are we going to control? So 0011 basically mean 4. To think about it. So 2, 1, 2, 3. 3. So we enable the 3 here. And now register A is enabled to input some value in, so we can put any value into our A with bus. So any value from the bus will go to A, but we have to take the value from any of this RAM. So that is strange. So what we have to do first is to read enable. Read enable the RAM. RAM read enable. And the value is from our register, so we output our sub op register first. Sub op register enable. So we enable our sub op register to output the value from it, which is the sub op is the address of the RAM we're going to load from. And next we're going to read enable the RAM. We read enable, it will take the value in, and then we have to enable the RAM manager actually. Double M. Then we have the RAM enable. So we enable our RAM, then the value will flow through our bus. After that we can run our control code over here. So enable the microcode. Microcode enable. So we enable our microcode, which is 0011, which is 3. It will turn on our register A to read the value from it. And then that value from the bus will store inside our register A. That is load A. Now let's try a different one. We need some pattern here before we can do anything else. So load B, basically the same thing. We load enable the sub opcode, and then we read enable the RAM, and then we RAM enable itself and microcode enable. Yeah. So basically it's the same thing, but the microcode is different. So this one is 0011, but the B one is the microcode is 0010, which is number 2 here. So we enable our load B. That is done. Now let's try a different one. So add So this is where it gets tricky. Let's try jump first, and we have to store A, store B, or something like that. So we have a, for example, the store C, which basically enable the value of C to the bus, and then we store it into our RAM. And I want to have the store A and store B too, but it's going to expand our control code and the microcode to get longer and longer, and I need more space for a different instruction. So let's just create the instruction of call it store C. Store C, which need a sub opcode, the 8-bit address of where is our RAM that we're going to store, which basically is VRAM. Load B also have to sub opcode. So what we're going to do is now we have some value in our register C. What we're going to do is to enable rec C enable. Now the output is coming from the register C to the bus, and we have to write enable our RAM manager write enable. So now we will take the address in. Oh, we're not going. Oh yeah. That is not good. That is not what I want it to be. So the address is in our sub opcode, so we have to enable the sub opcode first. Sub opcode rec enable. After we enable it, we have to write enable the RAM manager. RAM manager write enabled. So we enable the write, and now it will take this, and after that we have to disable our sub op register enabled. So how are we going to do that? So to disable it, we just need to disable everything. So the enable is 0, but we have extra step over there. The same here. So we have a sub opcode register SOR disable. Basically it just reset everything to 0. So let's call it output reset. So anything on the bus will become 0, but we have to disable everything. If we're doing the program counter, we have to disable the program counter to 0. That is very confusing. So what do we enable here? What do we the thing that basically we just need to disable our load the ROM. We disable the output and everything will become 0, and it disable the sub opcode too. Now we RAM RAM manager enabled, so we enable the output coming from the RAM manager. Where's the RAM manager? Here. So we still have additional if we write enable, we're going to write into our VRAM. I don't want it to write into our instruction RAM, but it creates more like a sort of a reliability, but it's more dangerous if we change our instruction. Let's say that we disable to like the ability to change our instruction, so let's change only value RAM. So if we enable our write, we don't need to enable our this thing VRAM. It will automatically enable our VRAM. But if we read, we still have to tell which RAM we're going to read from. So we can read it from VRAM or instruction RAM. But if we write, we have to write it into our VRAM for sure. So if we write enable, our RAM will automatically choose the VRAM. Let's keep that in mind. That is the purpose of RAM manager. Choose VRAM. Alright. Now we enable the RAM. It will take any value from the bus and store it in our VRAM. But the problem here is that we don't have any value yet. We want to store it from C, so we're not going to enable our RAM manager. We have to enable the register C. So we enable our C register. Now the C register will output some value into our bus, and then we have to RAM manager enable. That is a lot. So we have additional like step here. This is different from this one. The RAM read and write are different. Let's try a different wait, I should use some text editor instead. CD 8-bit. CD 8 computer. dir test, just call it test.text.txt. Now we can do it more cleaner than so. Load which basically has opcode, sub opcode.
Ooh.
Let's start by sub op register output enable. Let's say in English sub op output enable, and then we have a RAM manager read enable. and then we have to output reset, which is loader output disable. So all of this time it been enabled the whole time, our loader ROM. So it's enabled the whole time in a step that we're doing. And then we have to RAM manager enable, and then microcode. Enable, which basically 0011. In our example it could be different. After it is enabled, it will read it into our we will enable our register input, write enable, so our register will store the value. So yeah, and now let's go to the load B. So load B is the same, but the output enable is this, according to our architecture. And the problem is when we come to our store C that has sub opcode, should call it RAM address, so that we know the sub opcode is correspond to RAM address. This one too. So what we're going to do is we have to sub opcode output enable, VRAM write enable, RAM manager write enable, and then we output reset, which is loader ROM. Put the name properly. So the loader ROM will have to reset, disable, output it, disable, and then we have to register C output enable. After that we have to register C output enable, and we have to enable our RAM. This is where it doesn't have the microcode. We don't know where to put the microcode, so let's just write it, RAM enable. So the RAM enable it we can RAM enable first. We RAM enable in, and then we run the microcode enable. Basically tell our register C to output enable. Yeah, so microcode enable, which is 0.00 something 0, so what's going on here? We have the flag. We have the flag control unit that take this is different. So the flag control unit, we can use we use it to ask if it's 0 or not in case we want it to jump. Let's say that let's just say that our control unit connect directly to our C register C output enable. Let's say it's store C. I don't have the code yet. Let's just 001. Yeah, something like that. Could be different. So the pattern here is correct. No problem occur yet. So we have the sub up output enable, we have the RAM write enable and read enable. Oh, this is different, so we need to store it somewhere. So in the case of store we write, in the case of load we read, but after that everything is the same. So the load ROM is output disable, and then the RAM enable, and then the microcode enable. So we need a different microcode for the read and write, or we can just put like is it read or is it write. But now let's go to the jump opcode, which we got a address, basically 8-bit, to tell what address we're going to jump to. Jump address. But the jump one is a bit different. So the sub opcode is jump address. So sub opcode output enable, and then we don't RAM write. We're doing the program counter jump. So this is the short one. We sub up the output enable, we output enable the sub up. So now the bus will have some address, jump address, and the program counter we just need to enable the jump. So proc counter enable. It's only 2, so it's going to be a problem here because every other instruction has at least 4 or 5 instruction they're going to do, except with the jump. So we cannot group the pattern and then just run the microcode. We can call this microcode. Enable. Let not write the code because we're not sure what is it going to be. So the sub opcode enable is going to be everywhere, but then we have a different thing, which is loader ROM output enable and disable. And this instruction has a few clock cycle, but our jump has only 2. Let's talk about the add. We're which operation, or is it A, B, or something like that. So we sub opcode enable. But then our ALU will have to take that sub opcode in order to, so our ALU will automatically connect to our sub opcode, like connect to the bus. So if we enable our sub opcode, our ALU will know which instruction it's going to do, like is it add A and B together, or add A by itself, or add B by itself, or add A with C, something like that. But right now we cannot add A with C, big problem. We just say add A and A, B and B, and A and B. So we don't have to tell it which one, we just need to enable it. But wait, we have to microcode enable. So basically the value in the bus will have to flow from the sub opcode to our ALU. It doesn't really matter, just ALU, and it will not override by any of other value. You just need to enable this like a microcode, and it will add it. So our ALU has internal component that do this job first. So now we see that the sub opcode output enable is everywhere, but the load and the store has different pattern. It has additional pattern here. So what we have at the middle here. So basically the top and the bottom is the same, but the middle is to read or write enable, which we're not sure what's going on over there. We can say the load the ROM output is able in any one of this. Just to put it there so that we have the pattern easier to work with next time. Now the pattern is working, but yeah, because if we want to enable the loader, if we disable the loader, it will not affect any other component. But with the RAM enable, we cannot just enable it in any of this, because if we enable it, it will wait. But if we don't write or read enable it, will not going to write it to or read it. So we just yeah. We just enable the RAM for fun somehow. Just put it there. Maybe we can do something better than that. Now we have the problem with the write or read enable here. We have the read enable. So we can just say RAM neutral, which not going to do anything with the RAM. Then we're going to have like additional loader. So all of this is loader. Oh, okay, so it's if we choose the load A address, doesn't have the same pattern at all. Maybe the what is the other instruction that we can, let's talk about and the and the add. It's kind of the same, so don't want to do anything. The way we structure this is not right. But how long have we been streaming? It's been 2 hours. Going to end the stream soon, but gotta figure this out a bit before we're going to do that. So let's find some information how we're going to do this. The only thing we're going to need is Ben Eta. Still don't know how to pronounce his name, but he built 8-bit CPU from scratch. And where is it? Schematic. Yeah, here. Basically every component connect to each other with a bus, and then we already have he only have like clock, like it just a blink of from the clock from the program, either from the control unit. Yeah, everything all have like only clock, but this has a carry flag and 0 flag. We'll have to connect to the, what is this, the control unit, control logic. Okay, instruction register. We have to learn about this a bit more. So different from ours, very different, because ours is connect to bus, of course, but I don't want to talk about clock because it's only like one blink. It doesn't have any value that we can talk with our RAM or anything. So we have to use like this loader thing to tell the RAM what we're going to do, or to tell other component what we're going to do. So the clock is inside the control unit. It tell only to go next or to reset or something like that. We don't tell, like, we don't just blink it to our RAM to make it go next or back and forth or something like that. Yes, the control logic. Still don't know what is that, but I think it's very important that it's control the ALU. Is it the addition or subtraction, maybe something like that? And a lot of components connected to it. I think the control logic is the same as the way we connect right here, but ours is just connect directly to the component. We don't have another component that manage all of this. So if you have another component that could do manage this thing over here, may do the job. Well, we're going to look into that later, but now not sure what the hell that. And what we see here is that he doesn't have a register C. He only have a A and B, which connect directly to ALU to do the calculation, and then the value will directly go into bus. So we don't need to store C. Just load A and then do some addition, boom, and boom. We don't need additional register C enable or anything like that reduce the step, but it's still very complicated. Where's the control logic? Let's read about the control logic a bit here. This video is the heart of the CPU. It's what defines opcode and processor recognize and what happens when it's executing instruction. So I'm going to end the stream, and next time we're going to watch some of this. I'm going to watch by myself, prevent from getting copyright, and maybe we can learn a bit about this before we actually doing it. This is the instruction register, so we have the instruction from our here, so all of this will store inside the instruction too. Hold on. So yeah, I'm gonna save this. It is automatically saved. I'm going to end the stream. Don't need this anymore. Just save it. Left it there. And I'll see you later next week or something.